The surprising truth is that in modern electrification, the hardest problems are often not generation. They are interfaces, the boundary where power crosses from cable to air, coil to water, electrode to electrolyte, or market software to physical hardware. Start with what is already mature. Adjustable speed electrical drive systems, built around inverters, are proven industrial foundations. They let you shape torque, frequency, voltage, and power flow with high precision. So the bottleneck is rarely the idea of conversion itself. The bottlenecks cluster elsewhere. Switching losses show up as heat. Thermal rejection becomes a design limiter. Insulation ages under stress. Harmonic distortion spreads into neighboring equipment. Electromagnetic compatibility becomes a site-level problem, not a component checkbox. That framing matters for strategy because it changes what performance really means. Nameplate efficiency is not the whole story. Installed behavior, over time, is the story. A drive that looks excellent on a datasheet can become a headache in a dense campus. Put enough inverters into one port, mine, factory, or data center, and integration limits dominate budgets and schedules. Next, consider magnetic fields around overhead power lines. In 2025, combined shielding effectiveness for overhead power line magnetic field 3D models was compared experimentally. The key result is simple and uncomfortable. Shielding is not a single material property, it is a system property. Outcomes depend materially on three-dimensional geometry, conductor configuration, where materials are placed, and even the experimental setup used to validate it. For decision-makers, that implies a procurement trap. If your contract buys shielding material, you may not be buying shielding performance. Field containment can look compliant on a simplified test, then drift after rerouting, thermal expansion, maintenance changes, or load profile shifts. In dense power corridors, the right question is not, what shielding did we purchase? It is, what field map did we verify as built under real operating states? A third finding comes from fluid interfaces, and it generalizes beyond fluids. In 1994, radial finger evolution at the interface between two viscous liquids was modeled as a boundary element problem. That work is a reference case for boundary instability. The practical lesson is that an interface is not static geometry. It can evolve dynamically under forcing, and that evolution can dominate transport, mixing, and deposition. Translate that into modern infrastructure. Any process with a moving or deforming boundary can surprise you. Mixing steps can change yield. Electrochemical cells can shift performance. High heat flux cooling can flip from stable to unstable. Plasma-facing components can suffer localized loads. Even underwater power coupling can be limited by interface behavior you do not measure fast enough. So the interface itself becomes a state variable you monitor, model, and sometimes control. That brings us to a crucial distinction. Field energetics here is an umbrella term for disciplined energy control at interfaces. Conversion, transfer, containment, shaping, shielding, coupling, and deposition. It does not mean exotic energy sources. It does not mean reactionless extraction. It does not mean vacuum energy engineering. The constraints stay familiar. Conservation of energy, thermodynamics, Maxwellian field behavior, material breakdown, thermal gradients, and stability limits. If you are allocating capital, That clarity is useful. It narrows the near-term opportunity to engineering that can be validated. Better drives, better thermal paths, better insulation reliability, better measurement, better modeling, better controls. The near horizon, from 2026 to 2050, is mainly about disciplined adoption through replacement cycles, not instantaneous fleet conversion. Electrification diffuses because equipment gets replaced. Interconnections get permitted, and sites get upgraded in waves. Now add the coordination layer, where many leaders get tempted by clean abstractions. Distributed energy resources, prosumers, storage, and flexible loads can participate in markets. Coordination layers can improve system-level energetic performance, but only when they improve physical outcomes. In 2023, blockchain technology was proposed as an organizing tool for effective energy markets. The key word is proposed. It is not established here as validated universal infrastructure. So keep the boundary between market logic and physical safety very sharp. A price signal is not a protection relay. Settlement software is not an interlock. Dispatch optimization is not a guarantee against arcing, thermal runaway, or induced currents. Any market layer pilot needs auditable logs, regulator-readable behavior, and rollback-ready abort thresholds. Otherwise, you risk a system that is clever in accounting and fragile in physics. Where does this leave a senior strategist right now? Treat power electronics as strategic infrastructure, not commodity equipment. Drives, inverters, transformers, cooling systems, sensors, protection devices, and power semiconductors are reliability-critical assets. Put real budget behind three-dimensional field modeling, electromagnetic compatibility verification, thermal acceptance testing, and site measurement.